In this module, we will explore the third law of thermodynamics, along with its implications, significance, and limitations. The third law of thermodynamics, as stated by Max Planck, can be summarized in the following way. The entropy of a pure, perfectly crystalline substance, whether an element or a compound, is equal to 0 at 0 Kelvin. Different forms of the same substance, such as graphite, diamond, or fullerene C60, also have zero entropy at absolute zero as long as they are pure and perfectly crystalline. From the perspective of classical thermodynamics, choosing this common value of zero is simply a matter of convenience. However, the statistical interpretation of entropy provides a justification for assigning the value of zero to the entropy at absolute zero. The third law of thermodynamics can be understood using a statistical interpretation of entropy. At absolute zero of temperature, 0 Kelvin, thermal motion stops completely. All atoms, ions, or molecules of a perfectly crystalline substance are arranged in a perfectly regular, uniform array. In such a perfectly crystalline solid, each atom or ion is positioned in a highly ordered structure, leaving no ambiguity about their locations. As all the particles are identical and indistinguishable, exchanging the positions of two particles does not result in a new microstate. As a result, the crystal has only one possible microstate at 0 Kelvin. Using the Boltzmann formula and setting W equal to 1, we get the following result. Thus, at absolute zero, the entropy of a perfect crystal is zero. The third law of thermodynamics is only applicable to perfect crystalline substances and only holds at absolute zero. Any deviation from perfect crystallinity and purity, such as defects, impurities, or any residual disorder, will introduce multiple microstates, resulting in a non-zero entropy even at 0 Kelvin. The third law is important because it provides a reference point for the entropy of chemical substances. By defining the entropy as zero at absolute zero of temperature for a perfect crystal, the third law allows us to determine the absolute entropies of chemical substances at any temperature. In some cases, the entropy at absolute zero is greater than zero, indicating the presence of what is known as residual entropy. This occurs when multiple arrangements of molecules have essentially the same energy, so even at absolute zero, none of the configurations is energetically preferred. For example, in ice, residual entropy arises due to the randomness in the arrangement of hydrogen atoms around each oxygen atom. Each O atom is bonded to 4 H atoms in a tetrahedral structure with 2 short covalent OH bonds and 2 longer hydrogen bonds. Since there are multiple equivalent ways to assign these short and long bonds, Even at absolute zero, the system has many microstates with the same energy. This structural disorder at 0 Kelvin results in a non-zero residual entropy.